very much. Well, it's my pleasure and my honor to give a talk in this special session dedicated to the memory of Professor Smolyanov, who was really an excellent and brilliant mathematician, but also a friend. He was a really nice and kind person, always respectful to all. And let me show you some, sorry. Okay, some picture of him because I would like to share them. I would like to stress that even if I was not one of his students, I met him when I was quite young, and he always encouraged me. In particular, he insisted that I write the second edition of my book on path integrals, and I would say that without his encouragement, that project couldn't be ended. As some of you already know, I spent most of my scientific career in working on the mathematical theory of Feynman path integrals, and Professor Smolyanov's work in this topic was really fundamental. Here I put the front page of his book with Professor Shagulidze on path integrals, which unfortunately is written just in Russian. I often ask him to translate it into English, and I still hope that sooner or later someone will do this job. In this talk, I'm going to present the results of our only joint paper. This project began when he, together with Ivan Remitsov, visited me in Trento some years ago, and this is this picture together with Professor Andreatta, the chair of the International Center of Mathematical Research in Trento. Well, the original aim of our collaboration was the construction of Feynman or Feynman-Kac formulae according to his terminology, which are actually functional integral representation for the solution of some evolution equation. That's why in the first part of my talk, I will shortly recall some classical results on Feynman integrals and Feynman-Kac formula, as well as their generalization to the extensively developed theory of Feller semigroups. And then I will quickly move on in presenting the results of our joint papers, which are essentially three. The first one is the construction of a particular class of Feller semigroups on Riemannian manifolds generated by second-order differential operators. The second result is the construction of a particular class of Chernoff type approximation for these Feller semigroups. And the third result, which is quite interesting from my point of view, is the probabilistic interpretation of these Chernoff approximations, which actually allow to construct three families of random sequences of random walks on the manifold, which converge weakly to the Markov process associated to the Feller semigroup. And eventually, as a byproduct, let's say, of these results, which are more general, we can also handle the case of each semigroup and Brownian motion in the case of parallelizable manifolds. Okay, this is basically the outline. Then let's start from maybe the first proposal of a functional integral representation for the solution of an evolution operator, which can be found in the early 30s in the work by Richard Feynman, who proposed for the Schrödinger equation a representation for its solution in terms of an integral over the space of continuous path gamma with fixed endpoint. Here, the gamma represents a heuristic Lebesgue type measure, and the integrand is the exponential of the classical action functional evaluated along the path. Of course, this formula is just heuristic as it's said, but shortly afterwards, Mark Katz realized that one can give a rigorous mathematical realization to Feynman's idea in terms of what is now called the Feynman-Kac formula. Indeed, Katz realized that if one considered the equation instead of a Schrödinger equation, Feynman's idea can be realized in terms of a formula of this form, where the solution is given as an integral over the space of continuous paths with respect to the Gaussian-Wiener measure there of this kind of integral. And actually, one can look at the same formula from a slightly different point of view, in the sense that we can represent the action of the eighth semigroup of a suitable regular function f in terms of the expectation with respect to the probability measure, which is the distribution of the Wiener process starting at the point x at initial time. And nowadays, this is just the first and most famous example of an extensively developed theory which connects evolution equation and semigroups to stochastic Markov processes in such a way that the action of the semigroup can be represented by a formula like this one here. More precisely, let us consider the so-called well-known Feller semigroups, where we consider a locally compact metric space M and the Banach space of continuous functions there, which vanish at infinity, endowed with the uniform norm. And we say that a strongly continuous one-parameter semigroup on this Banach space made of positive construction is called a Feller semigroup. And this kind of semigroups are quite interesting also from a probabilistic point of view, since it is possible to associate them, a Markov process, actually with values in the one-point compactification of the metric space. In such a way, we can still represent the action of the semigroup on the functions belonging to this Banach space in terms of a representation formula of this form with respect to the expectation of where here this is the above-mentioned Markov process starting at initial time from the point x. Okay. An extensively developed class and studied of Feller semigroups are those whose generator is a second-order differential operator, elliptic differential operator, or this form, where Bi and sigma ik are assumed to be globally Lipschitz map, and this matrix A appearing in the second order part of the differential operator is constructed out of this function sigma by means of this expression. In this case, one can construct and describe the associated Markov process, which is a diffusion process, in terms of the martingale solution of a stochastic differential equation, and we can still write down a representation formula of this form. And this kind of result can be generalized toward the generator of the semigroup is perturbed by a multiplication operator associated to a continuous bundle functions. And in this case, the perturbed semigroup admits a representation formula of Feynman-Kac type of this form. Now, in our joint paper, we are concerned with a class of Feller semigroups on a particular metric space. In particular, we consider d-dimensional infinity Riemannian manifolds. We consider there a family of smooth vector fields and a differential operator, second-order differential operator, constructed out of these vector fields by means of formula of this form. So we have the first order term and the second order term, which is constructed starting by the vector fields AK composed with themselves. And in a local coordinate neighborhoods, if we consider the coordinates of the vector fields with respect to the canonical basis, the differential operator assume a rather familiar form, let me say. Now, this class of problem has been extensively studied, I would say, in the literature, but most of the results are restricted to the case where the Riemannian manifold is compact. And from our point of view, this situation is quite annoying because on one hand, we have an extensively developed theory of this kind of Feller-Dynkin diffusion on the flat space, on RD. Then there are nice results on compact manifolds. But the question is, can we provide a theory which unifies these two words? In other words, can we find a interesting class of Riemannian manifolds which encompass both the flat space and the compact manifold, as well as possibly other interesting manifolds? And the answer we found is extensively described in this fundamental paper by Shubin, who consider an important class of Riemannian manifolds and some interesting differential operator there. In particular, we consider the so-called manifolds of bounded geometry, and this is the precise definitions. We say that a smooth Riemannian manifold is of bounded geometry if it has strictly positive injectivity radius, and you can find some uniform bound for the k-fold covariant derivative of the Riemann tensor in such a way. And examples of manifold of this kind are RD, compact manifold, but also other interesting examples such as, for instance, Lie group and homogeneous manifolds, as well as the hyperbolic space and so on. And this kind of manifold enjoys some nice properties, many nice properties, I would say. One of them is the fact that they are always geodesically complete. Okay, now in order to state some important definition and results, we have to work in a nice coordinate frame, which is the well-known normal Riemannian charts. I shortly described them. We call the definition. So if you take a positive constant, which is less of the injectivity radius of the manifolds, then fix a point P in the manifolds, and the exponential map at P turns out to be a diffeomorphism between the unit ball with radius R in the tangent space and the open ball in the manifold made of all points whose geodesic distance from the point P is strictly less than R. And given this result, taken an orthonormal basis in the tangent space at P, we can construct a bijective map denoted by these symbols, which sends each point, let's say Q, in this ball, open ball in the manifold to into a point of RD in such a way, so the point Q is sent to the coordinates with respect to the basis of the vector in the tangent space, which is obtained as the inverse image of Q through the exponential map. And this chart is called the local normal Riemannian chart, centered on P, which is a nice coordinate frame and allows to introduce some nice definitions, in particular the class of the so-called CK bundle functions, which are maps quite smooth of class CK on the manifold, such that if you fix for any R0 that you fix less than injectivity radius, you can find some uniform bound on the derivative of the function f up to order k in every local Riemannian chart of this form, where these constants depend on the radius R0, but do not depend on the point P when you enter your chart. And this class of maps, the functions, enjoy some nice properties. For instance, you have this, let's say, equivalent characterization, which is some, I would say, nicer because it is intrinsic. It doesn't rely on a particular coordinate frame. So you have a uniform bound on their k-fold covariant derivative. Similarly, we can introduce the class of C-infinity bounded differential operators, which are those differential operators on the manifold that when you write down their expression in local coordinates in a Riemannian chart, normal Riemannian chart, you can find the uniform bound of these coordinates as well as their derivative, and this bound still do not depend on the point P where the map is centered, but just on the radius you are considering. Now, a C-infinity vector field on M fulfills also these nice conditions. So you have a uniform control on the k-fold covariant derivative of them. And you can also prove that whenever you have a C-infinity vector field and it is C-infinity bounded, then all its P power are C-infinity bounded as well. Now, given this, let's say, class of definitions, we can move on and stating one of the main results of the paper, which is the existence of the Feller semigroup generated by a differential operator of this form. More precisely, we are always working in a manifold of bounded geometry, and we are considering a differential operator that we call L0, which is assumed to be uniformly elliptic and constructed out of a family of C-infinity vector fields, I0, I1, up to IR of this form. We consider then a subset of our Banach space, dk, which is made of the C-infinity functions vanishing at infinity, which are CK bounded. And we can prove, first of all, that, well, this set of functions is dense in our Banach space. And moreover, if you consider this differential operator restricted to decay, then its closure, it's the generator of a Feller semigroup, and the generator as well as the semigroup does not depend on the index k. In other words, we have two results: the construction of the semigroup as well as a family of cores for it. This result can be generalized quite simply to the case where we perturb the differential operator with a continuous bounded function. Again, we have the result of the existence of the semigroup, which is still Feller, provided that this map is non-positive. Now, the second result of the paper is the Chernoff approximation. Now, Chernoff theorem is well known in the Russian school, and I just state it for the sake of completeness. what is a Chernoff type approximation. So we start by considering a strongly continuous semigroup on a Banach space B with generator L, and we consider a one parameter map, which from R plus to the set of linear bounded operators on the Banach space, which is strongly continuous, equal to the identity at t equal to 0, bounded in this way. And what is the fundamental property is number 3. So we require that on a suitable subspace of the domain of the generator, which is a core, this one parameter family of operator S behaves for small time exactly at the semigroup up to the first order. Okay, and according to this set of assumptions, one can prove that this composition of these operators approximate the semigroups in this way. And this vector is called the Chernoff approximation for this vector here, computed in terms of the semigroup. Now, in our case, following an idea of Ivan, we can actually provide a Chernoff approximation in terms of, let me say, a quite simple family of operators. Indeed, ST is given as the average of a family of shift operator, where this map here is just the solution of this initial value problem. In other words, these operators are just shift along the integral curves of the vector fields associated to our differential operators. And by using the assumption I stated above, bounded geometry, C-infinity bounded vector fields, and the theorem we prove, we are able to actually prove that that family actually provide a Chernoff function for this Feller semigroup. And let me say that in the particular case where the first order term and the multiplication operator vanish, there is an alternative version of the Chernoff approximation, which I like most because it's a bit more symmetric. Okay, last step is the probabilistic interpretation of this Chernoff type approximation. So the first remark is the following equivalent formulation of Chernoff theorem. But now, let us consider the case where the semigroup is a Feller semigroup, so it is associated to a Markov process, and we have this kind of representation. And now, assume that we are in this kind of situation. Assume that your Chernoff approximation admit a representation in terms to the expectation of some stochastic processes, not necessarily Markov. In general, they will not be Markov because this map is not a semigroup. And now, if this holds true, you can prove by actually applying an extensive developed theory that you can find, for instance, in this textbook, that this sequence of processes converge weakly to the Markov process associated to the Feller semigroup in the space of Cadillac path. Now, in our particular case, thanks to the particular form of the Chernoff approximation, which is given in terms of a very simple average of shift operator, we can construct a sequence of jump processes on the manifold, which have this form. So they are piecewise constant paths, and at each finite fixed time step equal to 1/m, the process makes a random jump and jumps from one point y to another point, which is obtained by moving along the integral curve of one of the vector fields Aj appearing exactly in the differential operator which generates our Feller process. Okay, so we are just constructing a random walk with a jump process where the paths are along the integral curves of these vector fields. And according to the theory I stated above, one can prove that actually this sequence of random walks converge weakly in the space of Cadillac function to the Feller process, Feller diffusion associated to the Feller semigroup. Now, we can ask for some more because we have in our hand a diffusion process, so we can try to approximate it with a sequence of random walks with continuous paths. And the main technique for doing this is contained, the main idea, in this paper by Smolyanov, by Secker and Vidic. We provide a construction of this form here, let's say piecewise geodesic interpolation of the path of the previous jump process. In this case, we consider this process sequence of processes Zn of T, which have paths which are piecewise geodesics. And the endpoints are exactly the one of the previous process. And again, we can prove the weak convergence of this sequence of processes to the Feller process now in the space of continuous paths. And we can do some more. In this case, we can prove another different convergent result. We can construct a different sequence of processes, random walk, again with continuous paths on the manifolds, where now the single paths are along the integral curve of the vector fields Aj instead of geodesics. And still, this weak convergent result holds. And as I anticipated at the beginning of the talk, as a byproduct, if we are considering a parallelizable manifolds of bounded geometry, in particular, if there exist on our manifold smooth vector fields such that in any point they provide an orthonormal space of the tangent space, then we can handle exactly with the same technique also the heat semigroup, the one generated by the Laplace-Beltrami operator, as well as the Brownian motion, since according to this set of assumptions, we can construct the Laplace-Beltrami semigroup exactly in the form we were able to handle before, exactly by composing the vector fields, the parallelizing vector fields of the manifolds. And in this way, we can still apply the former results. So we have that Laplace-Beltrami operator restricted to the former domain, the core that I described before, the one given by CK bounded functions, generates a Feller semigroup. The semigroup is independent of the core, independent on K, and the associated process, the Brownian motion, the Wiener process on the manifold, can be obtained as weak limits of random walk there. Also, and this is quite a new construction, by constructing this random walk as with paths which are along interval curves of the parallelizing vector fields. And I think I can stop here because my time is running. This is some references. So the paper by Schuving, the paper by Ivan on Chernoff approximation, the book by Etienne Kurz on characterization and convergence of Markov processes, two papers by Smolyanov and co-workers about this kind of techniques in the framework of Feller semigroup, and the paper which is going to appear in Mathematische Nachrichten. Thank you for your attention.